Okay, so welcome everyone. Uh, so today's lecture will be on combinatorial properties of disks. So I'll try to divide this lecture into two parts. So, so in the previous lecture, we looked at the independent set of intervals problem. And so there the properties of intervals were pretty straightforward. But now in today's lecture, so the final goal is to compute an efficient algorithm which gives us a good approximation algorithm to compute the independent set of disks. So that's the final goal, independent set of disks. But before we go there, we need to understand some combinatorial properties of disks. So the first half or the majority of this lecture will be about understanding these properties of disks. Okay, so let's get started. Just a quick reminder as to what an independent set is, because we'll be dealing with this. Let me draw a few of them here. Right, so if it's the unweighted case where the disks have no weights, then if I ask you what's the largest independent set, it'll be, say, these three. Right? So there are two cases that we'll look at throughout this lecture. One is the unweighted case. The next one is the weighted case. So in the weighted case, everyone has some weights on it. So let's just put some weights quickly. Say this has 5, 5, 5, 5. Say this has 1000, right? So then for the weighted version, the answer would be to report. So you have to report a independent set such that its total weight is the largest. So in this case, it will be this disk with weight 1000. Okay, good. So as we know the story, just like what I've told before, uh, so computing independent set is, again, exactly is NP hard. Right, so we will look for an approximation algorithm. Okay. So in today's lecture, we'll exploit the special properties of disks, which do not exist in all geometric objects, but those which are specific to disks, and obtain a constant factor approximation for disks. So one thing I should point out is that a lot of our discussion that we'll do today will actually extend to what's called pseudo disks. So what are pseudo disks? So most of the discussion, not all the discussion, at least the major theorems, lemmas that we'll prove will hold true for pseudo disks. The actual proofs might be slightly different or quite a bit different. But pseudo disks are basically curves which intersect at most twice. Like you have some curve, there's some other curve. So these intersect only twice, right? Like this. I'll say like this, right? So these curves just intersect each other at most twice. Maybe I should be specific. The boundaries intersect. So, but then, yeah, this is just a general remark. So we'll basically focus on this. Okay, but then the constant factor approximation will hold for the pseudo disk as well. Well, that's okay. Okay, so then, so the first half or the major part of this lecture will be on the combinatorial aspects Once we set the base, we get these combinatorial properties, then the second half will be on building the approximation algorithm. Okay, so that's the high-level overview. And so now let's focus on the combinatorial properties. Let's get started. Real properties of this. Okay, so the main theorem that we want to prove today is the following. So given n, so we'll look at both weighted and unweighted cases. So in 2D of total weight W, which means you add up the weights of all the disks, that will be W, and max depth less than or equal to K. So I'll define what max depth is. Please hang on. One can find an independent set of size at least n over k in the unweighted setting. And in the weighted setting, the independent we can find an independent set of weight at least W over K in the weighted setting. Okay, so what is max depth? That's very simple. So we'll need this definition going forward. So let's just carefully define this. So max depth here in this example is this portion has depth 3, because if you pick any point here, the number of disks that cover that point is 3. So, for example, it's 1 here, right? Because given a point here, the number of disks which cover it is 1. So in general, in this two-dimensional plane, given these 3 disks, the shaded region is the region which has the maximum depth. That is 3 in this case. Okay, so in general, we are saying, given a collection of n disks, the max depth, we are given an upper bound, saying that the max depth will be at most k, right? So given that, then we can always, and that's what we'll show today, is we can always find an independent set of size n over k. So this is very specific to disks, this property, because in general, this is not true. For example, I can show you examples where the depth is small. So in general, this is not true. General max depth does not imply large independent set. So that's what we are claiming, right, for this. Because we're saying if k is small, then we'll actually find a large independent set. Because you can easily draw some examples. Something like this. Right, and then So yeah, so in this case, I have shown an example where you can extend this thing for n objects and show that max depth is 2, but independent set size is just 1. Yeah, so I'm just showing it for 3, but if you're careful, you can ensure that every new object that comes intersects everyone which is already there, but doesn't increase the max depth. I mean, it goes up to 2, that's all. All right, so as you can see, there's something nice about this, which ensures that if the depth is small, then you can get a large independent set, right? Okay, so let's state the first fact here that we want to prove about these disks. So let me write down the statement first. The boundary of the union of n disks has order of n vertices. Okay, so there are a couple of things to define here. I have to define union, I have to define boundary. Okay, so let me draw some figures here. So you'll see a lot of figures in today's lecture because yeah, we're dealing with disks. Okay, so what is union, right? Oh, not good. So union is that portion of the two-dimensional plane which is being covered by these disks, right? So let me shade that region. That's the union of disks. So in the entire two-dimensional space, which is the portion which is being occupied by these disks? That will be called the union of disks, and that I have shown in this green shaded thing. Okay, so now what is the boundary of this union, right? So the boundary of this union, again, let me just draw it off. So we need some way to represent the union, right? This union is again an object, a more complex object than a disk, but it is still an object. So we need to represent it somehow, right? So the way to do that is by telling what the boundary of this object is, and that's what I'm actually drawing in red here. So if you see, the red portion is the boundary of the union. And now this fact that we are going to prove now is actually saying that if you're given n disks, then there won't be too many vertices on the boundary. Okay, so maybe I should define what a vertex is. Maybe it's obvious, but let's, for example, this is one vertex. This is a vertex on a boundary. These are vertex, and these will be called arcs, right? Boundary arcs. Okay, so this fact is saying that there won't be too many vertices, too many boundary arcs on the boundary of the union of the disk. Again, in general, this is not true. Well, you can just look at rectangles, tall and skinny rectangles. Tall and skinny rectangles. So I'm saying there are n over 2 rectangles like this, n over 2 like this. But now if you look at the union, well, okay, the number of holes, right? So the number of holes in this union will be quadratic. So that itself means that the boundary of this n square holes implies at least n square vertices on the boundary. Boundary of the union. So yeah, usually these tall and skinny objects are challenging cases to handle, whereas disks that we are looking at are more nicer objects in some sense. That's why we get this nice property that the union will have order of n vertices. Okay, so let me state this fact more precisely. It's a very nice theorem. It uses very basic geometric properties from high school. So that's why I thought maybe we should talk about it. Okay, so I'll call it a theorem because I think it deserves that name. Theorem 2. So I'm restating that fact more precisely. Please bear with me. So let D be the collection of n disks. This and 2D. Let U of D be the union of the disk in D. Now comes the claim, then the boundary of U of D Okay, there seems to have been some connectivity issue here. Hopefully we are back. So then the boundary of U of D consists of at most 6n minus 12 elementary arcs What is this? Yeah, the arcs are the ones that are defined in the previous slide, or the boundary arcs, whichever way you want to. And actually, this is not an arbitrary upper bound. This bound is actually timed. Okay, so let's go ahead and prove this. So to prove this, I'll have to start with a figure, and you have to give me a few minutes to allow me to draw this figure, because it's a, draw it very carefully. It's a big figure and needs some work. Okay, I hope I can execute this well, drawing figures. Yeah, so let me just draw a collection of this, and I'll set up some notation, and I'll show all of that in the figure. I think in total I have to draw 8 of them. Okay, we are almost there. 2 more have to be drawn now. Okay, the final one. Okay, so thanks for the patience. So now I've drawn 8 figures. And now what I have to do is I have to do some more work. So I'll look at the center of each one of them and label them. So for example, this is disk, oh, disk. Okay, first let's just draw the union of this, right? So the union of it will be this entire region here. And some more is hiding here. There's a small portion here as well, right? So yeah, so that's the boundary of, okay, I've not drawn it perfectly like here. Yeah, okay, because of shortage of time, I have to quickly do this. Okay, so the red part is the union. And now what I'll do is with every disk, we'll associate a center point. This is D3, this is P3. D1, this is D4. D6, D7, this is D5, this is D8. Okay, and then let's just, so we need to look at the centers of all of these. So then let's draw the centers. And this is not drawn to scale, so okay, so what I've done is for every circle, every disk, I'm looking at its centers. And now what I'll do is I'll connect some of these centers, right? Like this P1, P2, P4, I'll label them P7. Okay, I'll label the rest later. I'll join some of these PIPJs. The rules will be explained pretty soon. On what basis are they being joined? So we need this for the proof. That's why we are doing this joining business here. Okay, good. Okay, so now finally I can say I'm done with the drawing part of it. 5, 8. Okay, all right, so what I've done is I've joined some of the centers here. And first, let me verbally say what I'll write down the actual conditions later, but let me just verbally tell you how did I decide to connect some of them, right? So, for example, okay, you can't see my hand, but I'm saying that P2 and P3 are connected. Why? Because if you look at the disk D2 and D3, they intersect at 2 points. Let me mark them. Intersect here and here, right? So these are the 2 places where they intersect. And at least one of them, in this case both actually, but at least one of them is on the boundary. It's on the boundary of the union, right? So because, okay, there are two conditions to take care. First thing is D2, D3 actually intersect, which we can see. And once they intersect, they have 2 intersection points, which are shown in green. And at least one of them, as we can see, is on the union of this disk, on the boundary of the union of this disk. That's why P2, P3 got joined. Similarly, if you look at P1, P2, right? They have one boundary intersection point on the union. Right? Similarly, if you look at P3, P7, they have a reason. P7, P6, P6, P4, right? Like this P4, P1. Okay, let's look at one example where we didn't join, right? For example, we didn't join P8 and P5. Well, because the disks don't even intersect, right? So no chance of even connecting. Okay, a more interesting example would be P5 and P7, right? We didn't connect P5 and P7 because if you look at their intersection points, it would be P5 and P7, right? I hope I do this correctly. I think it is this and this. Yes, and actually none of them lie on the boundary of the union, right? That's why we didn't join P5 and P7. Good. So yeah, just to illustrate this, I had to draw this big figure. And now let me just formally write down how everything that we talked about just now. I'll just write it down. Let Pi be the center of disk Di. We will connect points Pi and Pj if and only if the boundaries of Di and Dj intersect, and at least one of the intersection points of the boundaries of Di and Dj lie on the boundary of our union, U of D. Right? So exactly what we discussed, right? That they have to intersect. And if they intersect, they'll intersect at 2 points. At least one of them should be on the boundary. Okay. It should be on the boundary of the union. Okay. Shouldn't repeat it so many times, but still. Okay, so the claim is, well, actually this kind of defines a graph, right? You can think of, see that this is actually a graph where these PIs are the vertices, and there are some edges which are connecting some of these vertices, right? So think of it as a graph. It should be pretty easy to understand that. Now the claim is that this graph that we have drawn now with these rules is actually a planar graph. Right? So for people who have not heard what a planar graph is, informally what it means is that you have these vertices and then these edges that you're drawing, you can draw them in such a way that no two of them intersect. Right? At least in this example, yeah, you can see it's planar because no two edges intersect. So the claim is that this graph, the resulting graph, is actually a planar graph, which means no two segments or edges should actually intersect. So it's not totally obvious why. Maybe in this example it's true, but in general, why should this be true? So let's actually go and prove this. Right? So claim is the resulting graph is planar, i.e. the edges do not cross. Okay, so now let's start proving this. So let's for I not equal to j, not equal to k, not equal to L. So just consider two edges or segments, whichever way you want to call them. Two segments Pi, Pj, and Pk, Pl. Right? Pi, Pj, yeah. So let's assume Vij is one of the points which is on the boundary of the union of D. Right? That's why. And then there's similarly we have one more pair like that, K and L. Pk and Pl. So they also have the fact that we drew these segments implies one of the intersection points of these boundaries have to lie on the boundary. So we're just labeling them. Right. So Vij, Vkl, both of them are on the boundary of U of D. Let me just write that down. Points on the boundary of U of T. Okay. So now, so do you remember what perpendicular bisector means? So that's what we're going to do. Draw a perpendicular, So now we want to show that these segments Pi, Pj, Pk, Pl don't intersect. So the whole work will be towards showing that. So draw a perpendicular bisector of Vij and Vkl. Okay, so say this is Vij, say this is Vkl, and let's say this is the perpendicular bisector. Right, so what is a perpendicular bisector? Okay, let me recollect the high school definition. You draw this line connecting Vij and Vkl, and then you draw a perpendicular line from the middle of this blue line. Right? So that's a perpendicular bisector. Let's call this line L. So if there's a point P1 here, which is to the, let's say, the left of L, then we can safely say that P1 will be closer to Vij than it is to Vkl. Similarly, if there's a point to the right of L, say point P2, then we can safely say that by definition of this perpendicular bisector that P2 is actually closer to Vkl than it is to Vij. Right? So P1 is closer to Vij than Vkl. P2 is closer to Vkl than Vij. Okay. Right. So this is the standard high school exercise. So now the question we want to ask is the following. So which side of L do Pi, Pj, Pk, and Pl lie? That's the question we want to answer. So let's go. Let's make one more claim. The claim is so this notation means distance between point Pi and point Vij. So that's the notation of using is claim is well. So we are saying Pi will be closer to Vij. Pi will be closer to Vij than it is to Vkl. So that's the claim. Why? Because if it was the other way around, if Pi comma Vij is actually greater than Vkl, then that would imply then the point Vkl will be inside disk di. Well, remember this point Vij itself is on the boundary of the disk di. Now, if you're saying some point Vkl is closer to Pi than Vij, then it has to actually lie inside the disk. And if it lies inside the disk, then we can claim that, and hence Vkl cannot be. When if you're inside the disk di, you cannot be on the boundary of UD, right? That's not even possible. So that was simple, right? So similarly, you can say this for the other points as well, right? So similarly, distance of Pj with Vij is, so Pi Pj is also closer to Vij, then to VKL, and it's the other way around for the other 2 points. PK will be closer to VKL. So all of this follows from similar arguments, so I'll just not write it. Again for PL as well. Okay, so what does this look pictorially? Pictorially it looks like this. So you have Vij, you have VKL, you have Pi is on this side. This is the line L, Pj, K, PL. So by these claims that we have made, Pi, Pj will lie on the left side of L, Pk, PL will lie on the right side of L, right? So then, of course, the segments joining Pi, Pj, Pk, PL cannot intersect, right? So that's the simple and nice high school geometry proof for it. That therefore, segments Pi, Pj and Pk, PL will not intersect. Okay, good. So now, because they don't intersect, we can happily claim that this graph is planar. Therefore, the graph is planar. And this is a standard property of planar graphs that I'm going to use now. And hence, so the property of a planar graph is that there won't be too many edges in it. And just because, I mean, intuitively, because you can't allow intersection of the segments, it cannot have too many edges. And hence, at most, 3n minus 6 edges / segments. Okay. So what does this mean? So this talks about the number of segments, right? But we are interested in finally in the number of vertices and arcs which are there on the boundary, right? But you can see that every segment can correspond to at most 2 vertices, right? Every segment here, you look at it, can correspond to at most 2 vertices on the boundary of the union by the definition of how we build these segments, right? Think about it. Not a simple statement to verify. So let me write that down. Number of vertices on the boundary of UD is at most 2 times the number of edges in G, right, which is at most 6n minus 12. And then it's easy to verify that once you have bound on the vertices, the number of arcs, call it elementary arcs. The arcs is also equal to 6n minus 12. So yeah, simple proof. So I thought, since it's a course on geometry, we should do some geometric proofs as well. So then this theorem here is actually saying that this bound is actually tight. Well, yeah, this might sound like an arbitrary upper bound, 6n minus 12, but actually people could figure out an example where this is actually true. So I'd not actually draw this. You can actually do it if you are a very good artist. But if you are someone like me, should I do it or should I just skip it? There's actually a tight example I have with me. Okay, let me just draw it anyways. So I'm drawing it as a strange figure here, but in general, you can always convert them into yeah. So you can actually convert each of these into a normal disk. Convert to normal disk. So basically here n was equal to 7, and you can see that there are 30 vertices on it, which is 6n minus 12. Yeah, you can actually count it. I did that and it came out to be 30. So this is just not an so this proof is actually tight. Right, so very nice. Okay, so that brings us to an end of this fact, theorem. And what was the theorem? Let's just recollect it. It basically said that the boundary of these on the union will only have order of n vertices, which is a very nice fact. We'll appreciate it later when the final approximation algorithm comes. Okay, so now let's move on. Okay, so now it's time for some definitions. I'm trying to see how I'm doing in terms of time. I think okay, yeah. This is going to be a long lecture, so okay, so let's move on and trying to define more stuff. Definitions. Again, let D be a collection of and this in the plane. Right, so now let's start defining things. The depth of a point P is the number of disks in D which contain P. That's easy to see, easy to understand. So now we'll define something which must be new for all of you guys, which is K level. K level is the locus of all the points in 2D with depth K. And next we'll have to define, so I'll actually show an example. Is the locus of all the points in 2D with depth less than or equal to k. Okay, time for quick examples here. Right, so this portion is level 1. Right, because the depth of the point here is, like any point here, the depth is 1. Right, so any point here, the depth is 0 by definition. And then let's take some other example. It says depth 3. Sorry, level 3. Right, so then, okay, I should be more careful in defining this. This is 1 level. This is 3 level. Okay. And then, so what is less than or equal to 2 level? That will be is equal to 1 level, sorry, 0 level plus, wait, yeah, plus 1 level plus 2 level. Right, so yeah, so that's the definition, right? K is where you're looking, K level is where you're looking at points with exactly depth equal to K. Less than or equal to K level, you're actually looking at the entire, that portion of two-dimensional plane where those points have depth less than or equal to K. Good. Okay. So then, okay, let me just, okay. I hope this is clear. So let me go ahead. Okay, so in some sense, we'll now try to generalize the previous theorem that we stated. Call it theorem 3. Let me write down the statement. The less than or equal to K level of D has order of nk vertices. Right, so what does this statement mean? I think I have to be a bit careful here. So I have to define what vertices are. So we go back here. So say if I pick this will be a 2-level vertex. This will also be a 2-level vertex. And this one will be a free level vertex, right? So in general, because you'll have many such vertices which are defined by the intersection of the boundaries of the disk, and everyone will have a different level number. So you want to understand how many of them will have depth less than or equal to k. Okay. So you're basically interested in these vertices now. That's the game going forward. And you want to understand how many of them have level less than or equal to k. Okay. That's what I mean by vertices now. Okay, so first let this is actually my, if I have to pick one, my favorite proof ever, I think it'll be this one. Let me just write it down. This is my all-time favorite. All-time favorite proof. And why? Well, the thing about this statement is it's a very deterministic statement that you're given this, you want to find an upper bound on how many vertices have depth less than or equal to k, right? And turns out the proof is actually via something called a probabilistic method, where actually we'll do some sampling, we'll play with probabilities, and then prove the statement. And the first time I saw this, it was a shocker to me because nowhere till now in this lecture we have spoken about probability. There's nothing right in this statement. It's a very deterministic statement. But it turns out if you want the most elegant and shortest proof, then it's via this probabilistic method. You can do it via other techniques, but they'll be quite tedious. But people took a lot of time to come up with this technique. But yeah, this is one of those proofs. Huh? It's via probabilistic method. And Clarkson and Shore, they wrote a couple of very influential papers from which this technique, this probabilistic method was known before, but in the context of geometry, they are the ones who had introduced this, right? So, okay, so after all that hype, hopefully you will also appreciate the proof. It might take some time for you to sink it in as, but okay, let's go ahead. Right, so first step here is you write down, pick a random sample R from this D. So you have a collection of these disks. You want to pick a random sample from it by choosing each disk independently with probability 1 over k. Okay, so now it's time for some definitions. So let V of R be the vertices of the boundary of the union of R. So you looked at this random sample that you got R, computed, it's not an algorithmic question, but you conceptually compute their union, and V of R is the set of vertices on the boundary of this union. Okay, so now let's compute an upper bound on the expected value of VR. right? So by the previous theorem, we proved that the number of, okay, let's do it more slowly. So by the previous theorem, we proved that number of vertices on the boundary of this will be order of n, which translates to this in this case, right? Which implies if I put expectations on both sides, I'll get I can bring out the constant. So now what's the expected value of the size of R? It's nothing but C of n times k because of the way we sampled, where we said we independently chose each disk with probability 1 over k. So the expected size of R will be n over k, right? So what we have done is we have come up with an upper bound on the value of expected value of V of R, size of V of R. Okay. So next what we'll do is we'll try to come up with a lower bound on V of R. Upper bound on this quantity. Right, so now let's again define some things here. Let's go back to our original KD be the vertices of depth less than or equal to K in D, right? Yeah, so as I said, this is the quantity of interest, right? Yeah, so this is the quantity of interest for us. So now what we do is we do the following. Fix some vertex V in this, right? And then define an indicator random variable for this xv, which is 1 if okay, so what are we saying? We're defining a random variable xv, and we are saying we're fixing some vertex v, right, in our vkd, and we are saying we're defining an indicator random variable corresponding to it, which will be set to 1 if this v, vertex v, happens to be in v of r. Right, so v of r we have already defined. Let's go and look at it again if you want. Right, v of r is the set of vertices which are on the boundary of the union of r in our random sample. So okay, so if I draw it as a figure, so this is the vertex v. Right, so if this vertex, So xv will be equal to 1 if the red disks are sampled in R, but none of the black disks are sampled. If that happens, then this vertex V will get to lie on the boundary of R, boundary of the union of R, right? So this is a crucial statement. Okay. So then now we can do some math again. So probability V will belong to V of R is, so this V is defined by two, as shown here, two red disks, right? These two red disks are the ones which define this vertex V. So both of them have to survive, which will happen with probability 1 over k and 1 over k. And then let's say there are j black disks. So none of them should survive. They should not be sampled. And I'm multiplying all of these because each of these disks were sampled independently. Right? So because these were all independent events, I could multiply all of them. So this is the expression I get. Now a simple lower bound of this is to replace j with k, because we know that the depth of all the points is less than or equal to, the depth of this vertex v is less than or equal to k, right? So that's why I can do this. And I'll say that this is at most e squared by k squared. So this is using a standard inequality which one should get used to. Right, so just replace x with 1 over k. All right, so if you do that, then you get this expression. Right, so that's the probability of a vertex v surviving and getting a chance to be in V of R. Okay, so then having computed this, now let's compute, therefore, so previously we had computed an upper bound on this quantity V of R, expected value of V of R. This time we'll compute a lower bound. And then, so since we care only about lower bound, so we can write this statement. So just think about this, right? So a vertex, okay, Vk of D. So vertex can be part of V of R. A vertex V, it could come from, could have any depth, right? So they could come from any depth. But since we are only interested in VKD, we can safely, so we are ignoring all the other vertices which can come to V of R. That's why we are putting this inequality. And we don't care about vertices which are not part of VKD. Right? So that's why I can write this statement. And now this will be equal to, can pull out the summation outside by the definition of expectation, and the expected value of xv, because it's an indicator random variable, is just, so I can do this times square by k square. So this is just standard calculation. Okay, so it turns out we are done. Right, so we had this equation 1 here, which gave us an upper bound on E of V of R. Now we have attained a lower bound on E of V of R. Now we just have to combine equation 1 and equation 2. Once we do that, equation 1 and equation 2, we get okay, let me write one more step just to add the dramatic effect. So this was one of the things we proved. This was the other thing that was proven. Right, so now we just have to combine the extreme statements here. It says Vk of D will be at most Cnk times k square, ignoring all the constants. This is just Nk, and we are done. So I don't know if you can appreciate this proof. Maybe you'll appreciate it a lot if we had done it through a very tedious technique which didn't involve probabilities. Right, and then if you had looked at this, maybe you would have appreciated it more. But even now, I think if you spend some time and imbibe what really went on here, then maybe you can appreciate this. So essentially, intuitively what expectation is really doing is looking at the average. In some sense, it's doing an averaging argument. And based on that, it is giving this bound. Right, so we are done with this proof actually. So we basically looked at this quantity VKD, right, which is what we wanted to estimate. We picked a vertex in it, and we computed the probability of it surviving in the random sample. Survive in the random sample and still be on the boundary of that union. That's what we did. From there, we got the lower bound, which was equation 2. It was some standard regular math if you see it enough number of times. And then we had the equation 1 was pretty straightforward, which followed from theorem 2. Maybe I should write that, right? So this followed from theorem 2. Right, so the union has linear complexity. And then we just have to combine both of them and we're done. So yeah, so this concludes the proof of my all-time favorite proof. Okay, so now, how are we doing on time? Should I go ahead and... Okay, so maybe I'll do one thing. I'll just stop here for the part 1 of this sequence. And then maybe in the next lecture, I'll prove one more fact about combinatorial property about this, and then come to the approximation algorithm. So, but that should be a shorter lecture than this. I think I've already taken quite a bit of time. So let me stop here. So let me just remind you that we want to prove this main theorem here, which we have not fully done yet. And we have come quite a bit, but still we have not proven the whole thing. So we wanted to prove this main fact. And this is what I'll do in the next lecture. Okay, thanks.